Welcome to lecture 32. In this lecture, we will continue our discussion on salient pole synchronous machine, or to be more specific, salient pole synchronous generator. In our last class, we have discussed about the main difference between a salient pole machine and a non-salient pole machine. Let's recap this once again. We said that this is a salient pole machine. This is basically used in a steam turbine where the rotor rotates at a higher speed. It basically has two number of poles, so it rotates at 3000 rpm, and since it has only two number of poles, the rotor is a cylinder. It has a small diameter and long in length. And on the contrary, a salient pole synchronous machine is used in a hydel turbine. Here it is used in a steam turbine, here it is used in a hydel turbine. By the nature of the turbine, hydel turbine is a slow moving turbine. So you require large number of poles on the rotor. So what we do, we make some projection, say this is my rotor. On the rotor, this is the shaft, and on the shaft I make some projections like this, and on the top of the projection I put the poles. Why I do this? Because I have to increase the space in which I will put the poles. For example, if there are 36 numbers of poles, I require some space, and to how I can make the space? If I increase the radius. So for increasing the radius, I make some projections like this. These projections are referred as the salient poles. What is the nature of this? The air gap is non-uniform. Here you see that this is the air gap. Wherever you go, the air gap is uniform. In this diagram you will see that the air gap here is this much, and in this space it is this much larger. So the air gap is non-uniform in a salient pole machine, and air gap is a uniform in a salient pole machine. So one more thing we have seen is that this has a smaller diameter, this has a larger diameter. And another thing is obvious, if it is smaller in diameter, it will be longer in length. If it has a large diameter, it will be smaller in length. So this we have seen in the last class. In this class, one more thing we said, that whatever analysis we have done till now is for non-salient pole synchronous machine. Whatever we have learned till now is for this type of machine, assuming that the air gap is uniform. Now we will take around 3-4 classes to understand this class of machine, that is known as the salient pole synchronous machine. Now before we go into salient pole synchronous machine, let's revisit something about non-salient poles once again. Now this is a non-salient pole synchronous machine, a basic non-salient pole synchronous machine. What do I mean by saying basic? That it has only one conductor on the stator and one conductor on the rotor. It is easy for us to understand if we make such simplification. This is not a practical generator, but it is easy to analyze if we make such assumptions. Now what is there? Here we have one conductor on the stator, so the direction of the flux or MMF produced by this current carrying conductor is in this direction. Say the rotor current is in this direction, so the rotor is also producing an MMF in the same direction. What is the angle between these two? The angle is 0. So how we write the power expression for power? Power is equal to E into V by XS sin del. What is del? The angle between E and V, or other way we can say that the angle between stator flux and rotor flux. Here the angle is 0, so it shows the diagram for a machine at no load. That is, the machine is not supplying any load. Let's come here. Here there is a finite delta. So what does it mean? That here the power will not be 0. You have E into V by XS sin del. Since delta is not 0, assuming other parameters are not 0, then there will be a finite power that will flow. So what I want to say is that as you vary the load on the machine, in case of generator it will be electrical load, in case of motor it will be mechanical load. As you vary the load in the machine, this delta angle changes. What is this delta angle? angle between the stator magnetic field and the rotor magnetic field. Now let's see how we have drawn the phasor diagram for this. What we did, first of all, we did phi f, that is flux produced by the rotor. Okay, if I remember correctly, we have written it phi f. Phi r was for resultant flux. So this was phi f. If this is phi f or ff, both are same. What is the relation between mmf and flux? Ff, this is mmf, is equal to reluctance into phi of f. So the relation between mmf and flux is a scalar multiplication by the reluctance of the air gap. So this is my flux. Perpendicular to my flux was E of f. Then I, that is the current that is flowing through the armature. Let's say this IA. If this is my IA, along IA will be my phi AR, that is flux produced by the armature. Here I have written as phi S. Let's convert it to phi AR. This is the flux produced by the armature or the armature reaction flux. Now this phi AR plus this phi F gives me the resultant flux. We call it as phi R or FR. This is how we have drawn the phasor diagram. Let me repeat it once again. First of all, we have drawn this rotor flux. Perpendicular to rotor flux was the induced EMF, and from between induced EMF and I there is some angle. Let this be the stator current. For this induced EMF, some current is produced in the stator. This is the induced EMF in the stator. Due to this induced EMF, there is some current. This angle is dependent on the power factor and the load of the machine. So let's say that this is the current. This current is flowing through this conductor. Since current is flowing through this conductor, some flux will be produced here. Let's say that this is my MMF or flux. Both of them we can write like this. If this is my flux, this is the flux produced by the rotor, this is the flux produced by the stator, the summation of this is the resultant flux. This is how we have drawn the phasor diagram for non-salient pole synchronous machine. Under what assumption we have drawn? We have drawn that whether my stator flux and rotor flux is here or at this angle or at some other angle, say like this, whatever is this air gap is constant. Since this air gap is constant, the reluctance that we have used to find the relation between phi f and ff or far to phi AR, this is for rotor, this is for stator. This reluctance is constant. Since this reluctance is constant, we can write phi AR and phi R along a same line only as a scalar multiple of this. Phi AR is a scalar multiple of FAR is a scalar multiple of phi AR. This we have written under the assumption that this reluctance is constant. Why we have assumed this reluctance is constant? Because the air gap is constant. The reluctance is mainly contributed by the air gap. Since the air gap is constant, we have assumed that this reluctance is constant. Since this reluctance is constant, we have used this equation and we have drawn the phasor diagram. Now come to this diagram. If you look at this diagram, this is the diagram at no load. You can see that the red line indicates your rotor flux and the black line indicates your stator flux. So let's rename it as our previous convention. Let this be phi f, flux produced by the rotor, and this is the flux produced by the stator. Let's call it as phi AR. So the air gap through which this rotor flux and stator flux flows, both of them are same here. Let's say that the reluctance here is R1. If you look at this diagram, the air gap seen by the rotor flux is constant. If this is say x centimeter, here also this is x centimeter. So the air gap that this rotor flux sees is same in length whether here or here. So the reluctance offered to the rotor flux will remain same. But what about stator flux? If you look at the stator flux, at this point the air gap is small, at this point the air gap is pretty large, quite large. There is a substantial difference between the air gap from this point to this point. Why this change is there? Because of loading. Here delta is equal to 0, here delta, this is your delta. When you have loaded the machine, the flux, the stator flux is seeing different air gap. At no load it is seeing some air gap, at load it is seeing some other air gap. Since the air gap here and here are different, the reluctance that is seen by the stator flux, I will write it as RS, reluctance seen by the stator flux. Here say this is RS1, this is RS2. This is the reluctance seen by the stator flux in this condition. This is the reluctance seen by the stator flux in this condition. These two are not same. Since the reluctance is not same, the flux produced by the same MMF will not be same. What we have written? How we have written? We have written like this: FAR is equal to reluctance into phi AR. And we say that this we can write as a proportional term, only a multiplication is there. But now in this case you can see here the reluctance here and the reluctance here is not same, so we cannot assume that this is constant. This relation holds good, but we cannot assume that this has remained constant. So the analysis of this machine is little different from analysis of this machine where the reluctance is constant. Here the air gap is constant, yet the air gap is not constant for the stator flux. For the stator flux, here the air gap is small, here the air gap is large. If you look here, the stator flux, every time wherever the stator or rotor flux goes, the air gap remains the same. So how to do that? Let's draw the phasor diagram once again. Since the rotor is seeing the same flux everywhere, same air gap everywhere, there will be no change in the rotor circuit. Let's see that this is my phi F, and corresponding to that this is FF and phi F, and perpendicular to this is EF. Up to this there is no difference. Let's see this. This was my phasor diagram for non-salient pole machine. This is the phasor diagram for the salient pole machine. First of all, we have drawn this for a non-salient pole machine. Same way. This was here. Up to this it is same. Let's say that the current is at some angle. Up to this also there is no change. Now what we will do, we will split, say for this there is a MMF. Up to this there is no change. Now what we do, we split this MMF along two direction. One, say this is phi ARD, this is FARQ. This is FARD, this is FARQ. This vector we have split it into two components. This is FARD and this is FARQ. What are these two components? These two components are 1 along E, another perpendicular to E. So if you look here, one along E, if this is my direction of flux, then this direction we call it as D. This is D. And sorry, this is Q. I'm sorry for this. This is Q and this is D. I'll draw it once again. This is the flux produced by the rotor phi f. Perpendicular to this is my EF. We call this direction, the direction in which my rotor flux is there, as D axis, and direction along E as Q axis. What does this word D indicate? D indicate direct axis and this indicate Q axis or quadrature axis. Now I have a current I like this that is flowing in the stator, IA. For this current there is a MMF FF. Now what we do, we split this MMF along two directions. One along Q axis, let's call it as FQ, and another perpendicular to this, we call it as FT. Now you see what happens if I call this as D axis. Along D axis my air gap is constant, and Q means perpendicular to this. Along this also my air gap is constant. The air gap is, as you move from here to here, the air gap varies, but along this direction the air gap is constant, and along this direction the air gap is constant. So I have a fixed value of reactance along this axis. Let's call it as XQ. Reluctance, if you better to write it as reluctance, RQ, and here it as RD. So if I divide it by RQ, I get my phi Q. If I divide this by RD, I get my phi D. So what we will do, we will take this MMF and divide it along two directions, and then we will proceed the way we have done for non-salient pole synchronous machine. So the method of analysis is not very different, but the only difference is that here reluctance has remained constant. Here reluctance, here we will define it as RD, and here we will define it as RQ, and then we will divide the flux or MMF along two directions, and then we will determine the flux. That is the difference. We will continue in the next class.